dk n, the sum of n dk n squared is known to have size like x log x k squared minus 1. There, remember that our main term had size x times log x 2k minus 2, so it's much smaller. So that's sort of a problem that we are losing too much here. But we can, so this is much larger. The main term, I mean, I haven't given you all the details of bounds we need for anything, but the point is that this is a troublesome bound because it's of size larger than the main term, which is of size x log x 2k minus 2. And that's why we can't take delta equal to 1 in that case, because we get into trouble by this Parseval bound, but we can take delta equal to half in that case, and then we have a 3/2 moment there, and we can handle it. So in theorem 2, when we have h to be small, 1, we need to take delta to be half. For example. And then we have to be very careful about this second sum. And actually that's the main input for the theorem 2, or one of the two main inputs. The other one is the doing S1, but S1 we already know how to do it because we have done similar thing for the real Wheeler function previously, and it's not too much different, but for this S2 term we have to be very careful not to lose any logs there, and we have to use duality and majorant for this divisor function and things like this in order to be able to handle it without losing any logs. So the result we prove for this related to this S2 is we prove the large value result for this sort of exponential sums. So this sort of result implies a result for the 3/3 moment, but I don't go into details about this, but this requires quite a bit of work to do this. But I don't talk more about it, but it will be in the paper, so you can see it there. But anyway, we have to be careful with the divisor function because of this issue that if we look at the second moment, then it will be larger than the first moment, which means that whenever we use Cauchy-Schwarz, we are lost. We always end up with the second moment of dkn, and then we lose some powers of logs, and then we are in trouble. And the reason we are really in trouble is that our saving in this S1 term is pretty small. So the usual thing in the circle method is to have some pointwise saving here, and use something like Parseval here, and then we are fine, but the problem is that when we are looking at small h, our pointwise saving is very, very small, which means that we can't afford to lose any logs here, which makes us sad. Okay, but from now on I will concentrate on this term S1, because irrelevant to the issues with S2, in any case we need to get some saving in S1. And for the von Mangold function, this is the main point, to get saving from S1. Also for von Mangold function, we lose one log from using the Parseval, but we will build many logs here, so it doesn't matter if we lose one log or not. And also if you look at the divisor function in the larger range, in particular if h is larger than log x to something tending to infinity, then we will be in lots of logs here and we don't have to care about losing some logs, but at this range of h being a fixed power of log x, we have to worry about losing logs there. But anyway, from now on I will concentrate on this S1. So in any case, we need to understand this S1. So what we need about this, that if we look at alpha, the integral of S beta squared d beta, and recall that this S beta is the exponential sum related to our sequence, so the an is either the one Vanguard function or the divisor function. So we need to study this, and let me finally say what we need about this. It's the bound like big O of over x times an squared. Okay. So anyway, we have to have some non-trivial saving here, and we need it for all alpha in the minor axis. And for approaching things like this, there is a lemma of Gallacher who says that if we look at this integral of the exponential sum of a short interval, it corresponds to looking at the thing in almost all intervals of length h. And we do this first. So we write alpha as a over q plus theta. So we take some rational approximation of a over q, and we know that we are in the minor axis, so we know that we can't have q very small and theta very small, and this theta is smaller than 1 over qq. And then we can use this Gallacher type lemma to reduce this bounding. Okay, I will write this down first and then say what's saying. So it reduces to looking at almost all intervals. I mean, we have a mean square over x here of length h. Here we have 1 over h, so it turns into intervals of length h. And looking at the mean of the an twisted by this e alpha n, because here we have that this integral is centered around alpha, so that this is essentially, we could write this as s alpha plus gamma per gamma that's 1 over h. But so this Gallacher lemma, which is based on Fourier inversion, it just has a few lines to prove that this, and so this, or this left hand side corresponds to this thing here, based on these exponential sums being constant on intervals of length h. But anyway, we just believe me, then I say that it's enough to understand this thing here. So we have to just do. And if we didn't have this exponential phase here, then this would be understanding or showing that almost all short intervals we have the correct asymptotics for the one Vanguard function or for the divisor function. But now we have this annoying exponential twist here that we have to somehow be able to handle. And one the thing one could do is, or what we will also do, is to write this alpha as a over q, and then we can reduce this to characters mod q, and looking at averages of characters mod q, and if we took q to be pretty large, like h to half, and look at this, we would actually end up with this previous result of Mikava and Bayer and R, which would give us this x to 1 over 3, but we want to do something better about this alpha, and that's why we will take pretty small q to be able to do something with the theta. Anyway, I will explain to you what we do next. So if we have a sum over short intervals, and then the typical thing is to use Perron's formula to get instead some mean values of Dirichlet polynomials, and that's what we want to do next. We want to transfer this problem of looking at things in almost all short intervals into looking at mean values of Dirichlet polynomials. So this reduces to bounding this, and furthermore to bounding. And let me write the expression that we end up with. So what happens is we use the Perron's formula, and then we integrate, open the square and integrate over x and get some savings there, but we have to use some stationary phase method to deal with this alpha thing and things like this. But anyway, what we end up after doing this and after splitting into characters mod q, so there's some technical stuff going on here, but eventually we reduce to bounding 1 over q times the integral of c around theta x. Then theta is this, alpha is a over q plus theta, and sum of mod q 1 over theta h times the integral from t minus theta h to t plus theta h of the corresponding Dirichlet polynomial. So we had this E alpha n here, and it was a over q plus theta, and this a over q goes into this sum over characters mod q, and this theta affects, then we use the integrate over